Gregory Cohen from Western Sydney University. Thanks very much for joining us on Australia in Space TV.
Hi, well, thanks so much for having me.
Wonderful. You're the Associate Professor, Deputy Director, International Centre for Neuromorphic Systems, or the ICNS, at Western Sydney University. Sounds much more interesting in terms of that neuromorphic systems, but I just mentioned off camera, I've been looking at some of the recent work that you've been doing and some of the videos, and we'll have links in the show notes to some of these, and if not, have some overlays. Some fascinating imagery that you're working on. Maybe introduce us to the ICNS and some of your key work, and we'll just get underway in terms of the key projects that you're doing.
Sure. So I think probably where to start is probably what neuromorphic is, because it's a term that it means a lot of things to different people. And I think everyone you talk to will give their own definition, but it is a term you'll start hearing more and more because it's definitely one of those exciting technologies like quantum computing where it's poised to change the way we do things. And unlike quantum, which has been 10 years away for the last 40 years, we're actually using neuromorphic technology right now. And there are products that you can buy in the shops that actually have neuromorphic technology in them, we don't do a good job of telling people about it. So neuromorphic engineering is really this idea of looking at how biology solves problems, taking those ideas and building real-world systems right down to silicon chips that try to approach sensing and processing in the way biology does it. And there's a great analogy that the director of ICNS likes to use, which is if you look at a dragonfly, and what's interesting about dragonflies is when they go and hunt things like mosquitoes, they don't go to the mosquito. They actually figure out where the mosquito is going to be and intercept them in midair. Now, that's a really complicated visual task. It's something that we really struggle to do with high-end computer systems. And a dragonfly does that with a tiny brain and a tiny amount of power. So we're doing it the hard way, and that dragonfly is doing it the easy way. So neuromorphic engineering is about saying, how do we understand that? We're not trying to build a dragonfly, but we're saying, can we approach computer vision? Can we approach robotics? Can we approach sensing in a more efficient way by looking at what biology does? And what we do here at ICNS is look for real-world applications. Now, I spend most of my time looking at space applications. So it somehow goes from biology and brain science to looking at satellites in orbit.
Well, I might start just on there. As you just mentioned, you do more in relation to space. Why would that be rather than sort of Earth-based applications and the like? Is it something just from a research point of view that you've found yourself doing? Or do you find that space is really one of those key applications that offer a lot more opportunity?
Well, it actually goes to the way these neuromorphic sensors work. They don't take great pictures. They sense changes in contrast. So much like biology, you need to specialize the sensor for what you're trying to do. Right. And it just so happens that looking up at space and looking down from space are fantastic applications for these sensors. When I finished my PhD, I was working in France in a lab full of mathematicians who were way smarter than me, and I came out and thought, I can't compete with them on the math side of things. Let me look for applications. And I'd love to say space was the first one I found. It was probably the 20th. But I put one of these cameras on a telescope to see what would happen. We accidentally saw a satellite, and then a light bulb moment went off, which was, hold on, we can see something in a way no one else can see it. And everything just built from there. So it was kind of an organic, which is kind of fitting for neuromorphic engineering, an organic sort of move into a really relevant application.
Well, you've been working with equatorial launch. There's, like I said, I was just looking at some imagery there, and we'll have some crossovers. Looking at how rockets are launched. Then you've got the neuromorphic cameras, 4 hours of a rocket launch, and then shrunk that down to 1 minute and 40. Fascinating. And then the full lunar eclipse was also very interesting as well. Are you using AI? Is it self-learning to a point in terms of how you engineer it based on neuromorphic, and then AI kicks in to learn? What's it actually doing, I suppose? Is there a black box of AI here in terms of understanding what it's doing?
So no, not quite. I would say there's 2 parts to neuromorphic engineering. There's neuromorphic sensing and neuromorphic processing. And both of those are related to AI, but they're not quite the same. Essentially, what we do and the way our system works is actually by changing the way the camera works in the pixel. So we actually add circuitry into each pixel that does the heavy lifting, which is the sort of change detection and logarithmic output. So different hardware. We don't actually use any AI in any of the work that we do at the moment. That's actually the next step. And in fact, when you sense the world in a different way and you produce far less data, but far more relevant data, you don't need as much deep learning and machine learning at the end to do classification and the sort of tasks you want to do. Essentially, we make our life easier by capturing only the data we care about. So we don't have to use these big AI systems to find the important data in the system. So
but there is still an element of machine learning and understanding the differences in the imagery, or is that just what it's capturing in itself. There's no machine learning required to detect those changes.
It's more the latter than the former. So we don't use a lot of machine learning. It's got to do with the fact that because these sensors are really fast and they only detect changes, you can move the sensor and get information when the sensor is moving. So if you know how you're moving the sensor, you can actually extract the information you care about. So you can use clever techniques by coupling the sensor and the movement of the sensor closely to the point that you don't actually need machine learning. You say, well, if you take one of these cameras that only sense change and you point at a static scene, you'll get no data out. If something moves, you only see those changes. So already you found the things you care about most of the time. But if, for example, you want to see things that aren't moving, well, that's easy. You just move the camera. And if you know how you're moving, all the static things will move in a correlated way. So you can do really clever things, really complicated things to do with conventional cameras and processing in a really easy way if you use a whole different paradigm of imaging, which is what neuromorphic sensing does. And that's what we do with the telescopes we use to track satellites, for example. And we also leverage that for some of our cameras in space when we look down at the Earth.
Well, maybe talk us through, you've got a camera on the International Space Station, or a couple of cameras, I think. Talk us through that particular project and how that's being applied.
Well, so that's a really exciting project. It's done in collaboration with the United States Air Force Academy, and it's a fundamental science project. So what we're trying to look at with those cameras is an atmospheric phenomena called transient luminous events, or sprites, as they're often called, which is one specific type of these phenomena. And essentially, it's like upside-down lightning. It's lightning discharges that go up into the atmosphere rather than down to the Earth. And they're really fascinating. They're really hard to see because they're very quick, they're very bright, and they also occur above the clouds, so they're kind of hard to see from the ground. Now, we put 2 cameras on the ISS about a year ago, and in fact, we're celebrating today the 1 year since we got the first data from those sensors, and they've been producing fantastic data since. And we just leverage the way these sensors work to see these really interesting events. And it turns out by just putting the cameras up there and looking down, we can do all these other really interesting tasks. We can image the Earth, we can see stars, we can see the horizon, and the data that's coming back from these is really exciting because these cameras are low power, they're high speed, and they produce very little data by comparison. So they're perfect for putting on orbit.
Is it a matter of not understanding what you're going to find when you apply these cameras, and then you have to kind of look at the imagery going, okay, this is something we're seeing, might be something we've seen before, but now we're seeing it in a different format. What's some of the sort of the highlights for you that has surprised you potentially?
Well, so the trick is that these cameras don't take pictures. They don't produce frames like a normal camera. You just get a stream of change events. And that's really interesting to work with. But the problem is that, we really haven't changed the way we do imaging since the first cameras were built. We just take a static image and we assume that's how everything has to be done. So we don't have a good intuitive sense of what data will look like in this new format. So what happened, for example, for the space station project is we had some ideas of what we thought the data would look like. We simulated it. We had lots of discussions. We got some actual data when it was on orbit, and it was unlike anything we expected in a very good way because there was far more there, in fact, than we ever expected. So, we've been able to see lightning from those cameras. We can see a whole bunch of Earth imaging. We have these great images where we take the data and we make an image that looks like a normal image, but it's really created by cleverly moving and shifting around the data that we get from the cameras. We can see boats, for example. And one of the interesting things, for example, is that unlike a normal camera, we can see both at night and during the day with the same camera, which is kind of like our eyes. When you go from an indoor setting outside, you don't have to sit down and change your eyes or recalibrate. You just sort of instantly adapt. And that's kind of what these sensors do as well. So, from space applications, they're fantastic. And, we're really excited at all the opportunities, both commercial and research, that come out of this technology.
Maybe on the ELA launches up in the Northern Territory, was there any takeaways? Is this something NASA and ELA had been doing before, or again, was this a new application for them to look at how the launch occurred and any potential outcomes for them?
Well, exactly. So that was just a bit of exploratory research that we did with ELA, and ELA were fantastic in supporting us with this. And the idea really is that because these cameras are really fast and only see things that change, we thought, well, what happens if we look at something like a rocket launch? Because we get all the benefits of having a really high-speed camera without that enormous amount of data. And if you look at those videos online, what you'll see is that what actually landed up happening was we put these cameras down in the exclusion zone, so pretty close to the rocket. And we had to leave because obviously you don't want to be anywhere near a rocket when it lights. But it sat there for about 3 hours before launch. And if you watch one of the videos, you'll see that at some point we see a shooting star. And the trick is we're capturing all that data as if we had a 10,000, 100,000 frame per second camera sitting there, but producing almost no data until the launch itself happens. Well, then there's something really interesting to see. We get this enormous explosion of data, literally from the explosion of the rocket. But that's all relevant information. So, there's some really interesting aspects about saying, well, if you want to monitor your launch and make sure that there's nothing in the exclusion zone, for example, or if something does happen or go wrong, we get to see it with a sort of unparalleled time resolution. And you can do things like put multiple ones of these cameras because they're really not expensive compared to, let's say, a high-speed camera you can buy commercially. So there's some really interesting applications in monitoring rockets. In the plume that comes out the rocket, that's extremely bright. Most cameras do struggle with things like that, but these cameras, the way they work, because they only sense changes, they can deal with the really bright flashes. And there's some really interesting things in assessing how the rocket is performing as it's taking off in real time. And that's the sort of things that come out of that work. So that's another whole avenue of research that we're really excited to explore with ELA.
And the other thing is you're making these cameras. The sensor itself and the silicon that's used is much changed from a conventional. How much difference is it from a conventional camera in terms of the sensor, and it's the processing that's the different point?
Well, so it's the actual sensor itself, the silicon in the camera is fundamentally different. So we have special circuitry in each pixel that does the change detection. So you basically can't use a conventional camera. We have to build the camera from scratch. Now, there are 2 labs overseas that have now started producing these cameras and spun out companies that are producing these cameras and looking for industries to use them. We're also designing and building our own cameras here in Australia specifically for space. So the companies that are making these sensors are going after other industries, sometimes the consumer market, the automotive market, but we're the experts in using these on space. And we're now saying, well, we want to be able to build and design these sensors specifically for space applications here in Australia. And we're actually doing that. We have prototype sensors, and hopefully on the next space mission that we have lined up, we'll be flying one of our own sensors soon, built and designed here in Australia.
Great. What's the pixel count or the resolution? Is it based on resolution? Is the measurement still the same?
It's still the same, but it's a bit different because the whole definition of resolution is kind of tied to the way conventional cameras work.
Yeah.
So we can get away with lower pixels, or less pixels, I should say, because we can move the sensor, and we can move the sensor across the scene and see a much wider part of it. And because we're so fast, we can move much faster. So we can compensate for having less pixels by just the way the camera works. Now, the current cameras we have about a megapixel resolution. And the good news is that we can leverage all the benefits and all the processes that they use to make these conventional cameras you find in your mobile phone. Those have just taken far more investment, but that pathway is open to us. So, essentially, we're just at the beginning of this road. So as these sensors develop, we're expecting the capabilities to get better and better and better over time.
So you will go for, say, 1 megapixel through to 2 to 5, and like as we've seen with conventional cameras, you're at 1080 at the moment?
Well, so we are, but there's an interesting problem, which is that too little data is a curse, but too much data is just as much of a curse, actually.
Yeah.
And there's a question to say, well, do we need all that to do the task? So I think the trick with neuromorphic engineering is to say, we make terrible cameras, but we make really good sensors for doing tasks. So if you can tell me the task you need to do, I can tell you the sensor, I can give you a sense of what that sensor will look like. And it may not need as many pixels as you think. And having more pixels just means more data, which means more power, which means more bandwidth, and not necessarily always the most efficient way to build a system. So if we want to build that Dragonfly, we don't want a high resolution sensor necessarily. We need the sensor that's just good enough to do the task it needs to do.
I suppose the other thing is the weight of the camera and the size and the sort of a payload for potentially either a robot or a drone. How big are the cameras?
No, you can hold one in your hand. They're tiny.
Nice.
In fact, at some point we're down to the size that we could potentially produce one the size of a GoPro quite happily.
Okay.
And that's one of our side projects here at ICNS is to do that.
And who are your key partners? Who from industry? We mentioned ELA, and that was nice of them, but sort of more commercial or industrial partners that you're working with?
So we basically are keen to explore this technology with anyone who has problems that they are struggling to use conventional cameras for. So, ELA was a really nice partnership, and that we've always had an interest in rockets. We work a lot with the United States Air Force Academy on the research side of things. So they've been a fantastic partner, and they just do fantastic work. Putting things in space is hard, and they make it look easy, which tells you, about the skills there. But I'd say we're looking quite heavily at space situational awareness, so tracking satellites from the ground and space junk with our astrosites, and that's a commercializable technology that we're busy looking at building companies and partnering to do that with both local and international SSA providers. The space-based research, we're looking at a bunch of local Australian companies who are interested in putting satellites in orbit. We've actually put 2 of these cameras up in orbit before with UNSW Canberra on that M2 mission. So each of those satellites had a neuromorphic event-based camera on them as well. So we had a great partnership with UNSW Canberra around that, and we were the first people to put cameras in space, these neuromorphic cameras, and the first people to get data back from the cameras in space, which, in the world of building satellites, is two different milestones and two big ones to achieve. And I'd say, Thales has been a great partner to us. The Australian Air Force, Plan Jericho, which is part of the Air Force, and their whole Jali program, where we're deeply involved in that, because the Jali character from the STEM outreach program is actually engraved in the top of the ISS payload we sent up. So we put Jali in space for the Australian Air Force, which is quite exciting. And
nice. I know we did cover that. From a research perspective, how big is your team there? You got PhD students here as well.
Mm-hmm.
Yeah, what's your research sort of team like?
So ICNS is about 50 people now. We started out with 4. And I will say we do a lot more than just space. So we have other modalities. So we do the same sort of sensors for audio. So we do these neuromorphic cockpits.
That was the question I had. Thank you. You can do this in audio too, right?
Yes, you can. And there's some really interesting applications for that underwater, for example, and just in problems like the cocktail party problem. Like, why can we understand people in a really noisy room? And that's an unsolved problem in science. And understanding how humans do it and how our auditory system works is actually a really important step in making sure that our home assistants can hear us when dogs are barking and cars are honking outside. So we do this in audio, we do this in vision, which is what I work on a lot. We do this in tactile, so touch. Essentially, you don't know your skin's there until someone touches you somewhere. And we even do it with smell. So we built electronic noses, which is a bit of a strange one, but there's no better way to tell a fish is going bad than to smell it, and that's the scientific way of doing it.
And how would you bring these together? And could you bring all these together, vision, audio, tactile, as well as smell, and stick it? I'm thinking, stick it on a robot, for example. And I've seen Elon Musk's companies and Tesla are somewhat working with this. They work in terms of that optical neuromorphic design and building their systems in this way. Where do you see this actually going, and can you bring all that together?
Oh, absolutely. So the trick is that everything is based on time. So these sensors really use time and the way they work. So, this idea of saying, instead of taking a frame rate or constant frame rate, you only get the data when it happens. That's really convenient when you have lots of sensors, because it just so happens that if someone claps, for example, you'll see it and hear it. And the fact that they happen at the same time is how you link those two events in your brain.
Right.
And the effect that things just happen, what is we say, at the same time or coincidentally, is actually a really easy way to identify things in the world around you. So we can build robots that can do really complicated things. For example, like hear a sound and quickly move to look at it, which is what our brains do, actually. We can do that with remarkably less power and computation than you would think with a normal sensor, just by exploiting the way the technology works. So, what does neuromorphic engineering lead to? Smarter robots, more integrated robots, things that can work and interact in the world we live in a way that current robots don't, because they're just not good at sensing the world. They're not fast enough. They're not nimble enough. Biology has solved this problem. We're sort of just borrowing those ideas to try bridge that gap in robotics. And space is a great application, and it's the way we're getting people to warm up to this technology, because people don't want to change. People have been using cameras for 50 years. Why would they try a new camera when they've got something that works? But when you say, hey, look, there's a great application. Here we're tracking satellites with a camera that can do things your camera can't. Maybe you should start considering this camera for your application too.
Well, I'm definitely of the conventional camera thinking in terms of surveillance applications. One question I've got is bandwidth. Sort of, we talk about that 1 megapixel. Is that the bandwidth that you require, and is there latency in this when you say it's time related?
So the bandwidth is interesting because it becomes activity driven. As I said, if nothing's happening, you get no data out. If lots of stuff is happening, you get lots of data out. So the bandwidth changes, and that makes designing the systems harder. But it also means that if you're looking up at the stars and nothing really should be changing, you get no data out. And then if you see a satellite, you only get the satellite. So you can imagine how much less data you get than taking pictures of the sky, where most of your pixels are just empty because there's nothing there that's bright enough for you to see. So the bandwidth, the actual amount of data you produce, is orders of magnitude less than a normal camera. And in terms of latency, these cameras are incredibly fast because you don't have to wait until the camera pulls the frame out. When a pixel sees a change, it goes, here's the change, and that can be within microseconds. So we have a fantastic camera that has low latency, has extremely high sensitivity to changes, and can get a whole lot of those changes out very quickly when it needs to. But most of the time, if nothing's happening, you don't have to do anything.
Wonderful. Well, look, I've got a million other questions. We could literally talk all day. It's a fascinating field. What's your outlooks for 2023 or beyond, and any call to action that you'd like the audience, if they want to get in hold of you, or any potential researchers or any commercial sort of runaways that you might have? Yeah, over to you in terms of highlights.
Well, absolutely. So, I mean, we've had a great 2022 in terms of neuromorphic engineering and our space research. 2023 is going to be even better. We have future space missions. We have more rocket launches. We have so many exciting and interesting projects. And in the next few weeks, we're going to be doing a pretty big campaign to find new people. We need 10 PhD students, 3 or 4 postdocs, technical officers, research assistants. So we're going to do a big push to really hire and grow our team. So if anyone is interested in a career in neuromorphic engineering, in space engineering, in neuroscience, in electrical engineering, or any of those sort of fields, neuromorphic engineering is a bit of an odd field that crosses so many disciplines. Anyone with an eclectic background is probably a good fit. So please reach out. We're really excited. We really, really want to grow this team. And this is something that we're doing here in Australia. We're the largest neuromorphic group in the world at the moment. We just want to grow from strength to strength. So come join us if you're interested.
Wonderful. Associate Professor Gregory Cohen, Deputy Director, International Centre for Neuromorphic Systems, or the ICNS at Western Sydney University. We'll have the links in the show notes, and we'll use some of the footage as overlays in this particular session. But otherwise, you can go to westernsydney.edu.au/ICNS. Absolute pleasure, Greg, and all the best for the rest of your research for the rest of 2023. But we'll definitely keep tabs on this. It's one to watch.
Fantastic. Thank you so much.
Thank you very much.